this work focuses on creating a product where it's able to understand the search results returned from the web rather than with the current technology of whether that be SEO or Google's current algorithm. And just to give a quick introduction about the people who have worked on this is me, Ruiyi. I am currently a high school senior from Troy High School in California, and I was mentored and helped very profoundly by Carlos Gonzalez, a current graduate of UC Berkeley and a comp sci department employee of the California State Polytechnic University in Pomona. To first, to first give you the background on why this was created, I will move to my slideshow. So the problem many face is that with current existing search engines, although it has had great success over the past decades, it often fails to capture and return the users with the information they're exactly looking for. For instance, some users might waste time skimming through lots of technical details when they simply hope to have just an overview, and the vice versa. Hence, we believe that with the recent innovation of LLMs and the maturity of GPT or other NLP technologies, we believe that this problem could be drastically improved upon with uh, scraping and understanding the websites returned currently by Google and reanalyzing them based on their complexity so that the user can be returned with the search queries and search results that they were initially intending to look for. So we done this through using the state-of-the-art transformer models. Uh, I will go into which one we use in the very distant in the very near future. And here's this design overview of how things will work. Okay, next slide. And to go into some details on the shortcomings of current search engines, the SEO practices, which is which is heavily relied upon by current search engines, often involves manipulating the search engine results, and this occasionally leads to quality content being obscured from the SEO because of SEO, which hinders both researchers and daily users. And 74.3% of link builders pay for links, and 66.5% of all links on the internet are currently dead. And the top Google results get 27.6% of clicks, while beyond the first page, only 0.63% are ever interacted upon. And frequently, some of these contents may prove very valuable in one's quest in finding the information that they are looking for. So I want to go into some challenges that me and my team have faced throughout the creation of this paradigm. Uh, the first is the anti-web scraping and search efficiency difficulties that we faced. Many websites are currently on the internet have their own policies on preventing automated web scraping from happening to their website. And this is often done through the use of reCAPTCHA, as well as their algorithm on noticing repeated access from the same IP address. So this greatly hindered our progress in creating this, as we required the first 50 results to be scraped by our algorithm to be analyzed and ranked. Therefore, we first implemented our own rotating proxy system with an array of with an array of unique IPs that is often reassigned after every two scrapes, the IP will be rotated. And we also have faced problem with practical search speeds for users because current search engines are extremely efficient, where it only takes around 0.5 seconds or less to be returned with all the search results. And we understand that in order for our paradigm to be practical and usable, having a search speed under 2 to 3 seconds will be essential and important for the user's practical needs. So this is why we created our advanced multi-threading algorithm to enhance browsing speed. So given our cloud's CPU capabilities, with I believe 12 cores, it is able to consistently execute the searches in less than 1 second. And I will go into the exact statistics on how long it will take the entire pipeline to run in the very near future. So the second major challenge that we faced was data-related difficulties. Because of the nature of this endeavor, there isn't a existing data set with websites on the internet that is related to research questions or daily questions with complexity score ranked uh, that fits our criteria. We needed to create our own data set. And this was a major challenge because in order to train a model like DistilBERT, a large amount of data is needed for a quality model to be fine-tuned and trained. And additionally, there's this problem where certain websites are created with extremely complex and unique HTML, CSS structures, and that leads to occasional failed scrapes, whether that yield content that is often mixed around because the algorithm isn't able to identify where's the top, where's the body, where's the end, or some websites have very deep and intricate uh, navigational menus that creates a noise in our system. So to resolve this problem, uh, we use Roberta, which is a model that is specialized in understanding a text legitimacy and a text grammar syntactical ability, well, syntactical ranking, essentially returning essentially returning the user with information on whether this website is whether this content is real English or whether it's just random words put together. So this Roberta we train on COLA, and COLA is the corpus of language acceptability, and it's a data set which we train Roberta upon. And the third major challenge that we faced was the transformer model's token limitations. So for DistilBERT, 512 token li DistilBERT has a 512 token limit, which poses a major challenge for longer website articles, as most websites contain more than 512 words, especially for topics that involves especially for complex topics in the science, tech, engineering, or math field. And this is relevant. This problem was relevant for both the dataset creation and the complexity ranking of our DistilBERT model itself. And in our research, we found that the sliding window technique can preserve context, but it is extremely computationally inefficient. So for context, sliding window technique is a technique where a large passage of text is truncated into overlapping sections. So say a text has 1,000 words, it would have a section with the first 250 words, and then it'll have another section with the 200 from the maybe 150 words to 300 words, creating a 150 word overlapping of text. And this will repeat until all the text has been included in this new truncated corpus. And this will be repeatedly passed through to the model to maintain context. However, this is impractical for our cause because we require an efficient speed while maintaining high accuracy. So this is what prompted us to create our trisection sampling technique, which we extracted the first 50 words, middle 300 words, and last 50 words of the website, and we recorded the length of the website to capture further context upon uh, upon how much content is in the website as a whole for our future DistilBERT transformer training. And moving on, here's a system overview of how exactly everything works. So in the very beginning, our our web scraping algorithm reaches out to Google and retrieves the top 50 results of the query that the user decided to input from Google. And then each website will be web scraped and processed into raw HTML data and further into interpretable content through our pre-processing algorithm. And this will be further expanded upon in the future slides. And the original URL, domain, and title will be preserved into a pandas data frame, which uh, into the pandas data frame, which will be saved into the CSV file for future usage, which is going to be used in the results presenting area. And then this interpretable content, which is from the raw HTML, is then truncated with our trisection sampling technique for further analysis. And before passing into our DistilBERT model, we go through a stage of content understanding through Roberta, which is trained on Cola to determine if the text is legitimate and worthy to, to be analyzed by our model. And this improves the speed and efficiency marginally and occasionally drastically because of the level of variance in terms of web scrapes. And after after the complexity ranking from the DistilBERT, our API, which is in associate with Google Cloud, will return a JSON file containing the .csv file we mentioned on the second stage with appended complexity scores, and it will be interpreted and presented on our website through our domain. And to go into how the overview of the data processing aspects, first we utilize regular expressions, which we utilize it to extract a domain name, URL, and title to extract detailed and important information on each of the websites to be stored and analyzed by our model. And we also remove latex expressions from regular expression with regular expressions to avoid any confusion our model may face. And secondly, we use natural language toolkit NLTK to and we use their stop words data set to eliminate noise in raw HTML data. And finally, as I mentioned, we use Roberta, which is capable of determining text legitimacy to remove websites with failed scrapes. And on the right, here's a picture with some common stop words. There's many more that's included in the data set, but here's some stop words to sort of give you an idea of what kind of words are taken out from the text to improve efficiency, gather more content, more meaningful content for a model to analyze, and etc. So next slide, I will show you what it will look like for a raw HTML and what it will look like after our data processing. So this is before any data processing with just the raw HTML scraped. As we can see here, it contains a lot of course, HTML tags and stop words. If you look at it, it says machine learning powers a variety of key business and use cases, but how does deliver competitive advantage among machine learning and et cetera, right? And after the pre-processing, uh, it is quite apparent that many stop words are removed. So I will read a random sentence from here, and it will be very obvious that the stop words have been removed. So say the sentence of model customer churn through machine learning, acquiring new customer is more time consuming and costlier than keeping existing customers and loyal. So like stop words such as a and others have been removed to enhance it. And the next is the data generation process. So in accordance to our second challenge of the problem with the lack of an existing data set, which we could train our model on, we had to first use GPT-4 to create 300 unique queries that is linked to STEAM subjects and research questions and daily questions. So over the course of 17 days, over 20,000 websites have been scraped and analyzed by GPT-4. And over this process, over 5 million words were gathered. And this was our minimum threshold for a data set that is capable of training in a large and advanced model such as DistilBERT. And prompt engineering was used to enable transparent, objective, and consistent complexity ranking with GPT. And these three things have been consistently known to be GPT-4's worst enemies in a sense that often it is not transparent in how it came to its answer. And objectivity is very important because every website has to be ranked in the same manner so that our model is able to create a very accurate interpretation of each of these unique websites, whether have seen it or have not seen. And lastly, consistency, as I've mentioned, is of the crucial importance. And GPT often fails at these three things. So that is why prompt engineering was taken in consideration to avoid these problems. So here is the 5 major points that we sort of take into account to rate to rank the complexity. And the first one is the frequency and complexity of specialized terminologies. And the second one is the sophistication and profundity of conveyed technical notions. And the third one is the cognitive requirements essential to grasp the subject matter. And the fourth one is the length of the website content, indicating the scoped content. And I want to emphasize that this is very important as we used our tri-section sampling technology to only maintain the first 50, middle 300, and last 50 words. Hence, without this information, our model will be blind towards the true length of the website, whether that be 500 words or 2,000 words, which often have significant implications upon how complex and how intricate and how deeply a website explores certain content. And lastly, we also take into account the projected target audience of the websites. And in accordance to resolving some of the issues mentioned in the slide before, we in our prompt we utilize the concept of explainable AI so that the LLM or GPT-4 in this case can iterate its own thoughts and inspect its own thoughts to improve its conclusions and its consistency. And moving on, I wish to quickly talk about the model architecture and the training process taken up. And the model architecture we decided to use was DistilBERT. And the reason why we decided to use both this model and encoder was because of its extremely high accuracy and power while maintaining very high efficiency, which again is crucial for our paradigm as we wish for it to be practical. And to give you an idea on the specifics of why DistilBERT is so powerful while being so efficient is that it maintains it maintains 97% of BERT's performance. And BERT has been known as the state-of-the-art model in terms of NLP, and it is one of the most powerful, one of the most accurate, as well as a relatively efficient model. And DistilBERT takes advantage of all the performance BERT was able to accomplish over its years, while cutting down 40% of its size so that it's only 60% of its size. And throughout training, we decided to use the Atom Optimizer, which has over the ages been known as the most powerful and essentially the best optimizer to use for tasks like these. And we utilize MSE loss as our complexity ranking is a float from 0 to 1. So that was the most appropriate MSE loss. That was the most appropriate loss function. And we trained 20 epochs on the data set with over 20,000 sets of data, which is 20,000 websites, each encompassing around 400 words. And the model is trained to handle up to 512 tokens given the original constraints of the DistilBERT model. And on the right, here's a picture giving you a brief overview of the structure of the DistilBERT. And moving on. So here is the final pipeline. Just a quick summary about how the final pipeline of web deployment has been done is that number one, it's easily deployable in collaboration with Google Cloud because of the nature of its app engine. So it can be easily accessible and deployed by others interested in utilizing our research. And it is also highly efficient. Through our testing, we've found statistics to average around 2.3 seconds total runtime for the entire pipeline from the moment the query is inputted to the moment that the results are returned with a 500 Mbps download bandwidth. And it scales well with hardware and creates we created an API and it's currently deployed on our web. However, right now we have scaled down the speed of the web to lower costs. And to talk about a few, well, before I do this, I want to quickly talk about some of the experiments we ran to determine problems and future improvements that could be taken upon this current paradigm. So I will switch my screen to this. So the first experiment, essentially, we wanted to find, excuse me. So for the first experiment, we wanted to sort of find the discrepancy of websites that does not fulfill the criteria of being 400 words long, as certain websites, especially websites containing sort of daily searches, often contains less information than 400 words. So we designed an experiment to conduct to find the loss in accordance to the word count of 400 words and anything less than that. So here we looked for I will see if I can zoom into the table. I apologize for the low quality, but you can easily observe here that at 400, the loss is around 0. 0.025, which is very consistent with our training and validation loss throughout our model. And that demonstrates that with even new websites that our model is able to perform well. However, as we see that when there's more blank space for websites with lower word length, the loss drastically increase after 320 words. However, from the section with 320 to 400 words, the loss is it's relatively consistent, averaging around 0.04 to 0.03. And this is a good sign as we've analyzed that relatively low websites have have words less than 320. Therefore, a majority of websites will experience a low loss with our model. And to move on to that second experiment, second experiment, we wanted to analyze how our model performed in accordance to different categories, and to notice the bias that our queries, the 300 queries derived by ChatGPT, and the training data and the data set created upon that, and its effects on how our model performs to different areas of likely of of rather non-STEM related queries. So we chose 5 different genres that hasn't been touched very closely upon our training data. And we chose politics, fine arts, fiction, blog post, and food. And throughout this, we've noticed that, to zoom into the table again, uh, the red line is our training validation loss, which, as I mentioned, is around 0.025. Uh, for politics, it averaged around 0.04, and fine art 0.05, and 0.06 for fiction genre, and 0.045 for blog posts, and around 0.055 for food. And this is definitely very indicative of our model's lack of experience with certain genres of text. And this indicates that for future research, we wish to include a bigger data set with a greater variety, or we also plan on training a completely separate model to analyze different categories of text so that each model will be able to retain its very high performance in its natural environment. So therefore, this leads me to sort of discuss one of the aspects of our future areas of research that we wish to conduct, which is to which is to train multiple models of DistilBERT on different data sets and have an algorithm that's able to interpret and determine which category a website is, and send the content to the respective model for analyzation. And here I wish to talk about the related works that essentially wants to resolve the same problem as we do. And one of the major ones is Google's SGE, which is Search Generative Experience. I'm sure that many of you have already noticed this with Google's sort of current implementation, where given a question that one asks, it will have a section on the very top of Google that essentially writes you a summary in real time, just like ChatGPT and other large language models. And although this does provide the user with a very quick and clear understanding of what they're looking for, it often fails to provide the user with a website that is credible, that fits their level of intended complexity. And this is attributed to the fundamental nature of SG, as the websites it selects and cites for AI generated response completely disregards the user's intended level of complexity. And the second sort of major the second related work that relates very deeply to what we're doing is traditional linguistic complexity rating indexes, such as the Coleman-Liao index. And in fact, in the very beginning of our research, we considered implementing areas of the Coleman-Liao index uh, to sort of adding a weight to our complexity ranking algorithm and our formula. However, we decided that it was inefficient, and we believe that just the model itself is able to yield more consistent and accurate information. So to discuss into this, the Coleman-Liao index basically uses the letters per 100 words and the sentences per 100 words to essentially estimate how complex a text is. So essentially, to break it down, if you consider that a word that is very long, such as computerized, versus the word, or which is the word of like the, a passage with more long words is generally going to be more complex than passage with many short words, and that's been proven historically through English especially. And the reason why the Komei-Lau index is very competitive is that what it does is that it increases the efficiency of completely formulated computerized scoring, as it bypasses the need to analyze syllables or other niche areas of language that often takes the computer a lot of time. And the next one is a highly technical and very powerful way of analyzing text complexity that converge very intricately with our approach. However, well, before I say that, this approach is called the latent semantic analysis, or often known as LSA. And this technique serves to uncover obscure relationships between words within large sets of text by employing a singular value decomposition. And essentially, this technique delves into like the linguistic attributes of text that extends beyond just the surface level of the patterns of words, but rather it captures the very deep intricacies of the language itself. However, there's various restrictions that limit it from working in a situation as our paradigm does, because it requires substantial computational resources for processing, especially if the corpus size is large. And given that the nature of the search is 50 websites, the corpus is extremely large, and to be able to conduct LSA in a timely manner is relatively impossible unless given a very powerful computer that is often not accessible on cloud for the majority of researchers like me. And the second problem is that LSA is very static in its nature, which means that once the analysis is performed, it does not learn or adapt from new data, which is very restricting and limits the model's potential for future improvements. And I want to talk about the impact of this research, and is that it enhances the efficiency in information retrieval because users can now access relevant information faster, which saves time and reduces cognitive overload, which many of us have experienced in our personal experience with the internet. And it improves the accessibility for varied user groups, whether one is looking for simple information that they want to quickly understand, or a researcher is interested in finding complex information that they wish to incorporate in their own research. And thirdly, it encourages informed decision making, which educates and influences users to make more informed choices on what they want before entering a search. And additionally, it fosters a deeper understanding, which often shines light towards the more complex topics explored on the internet by allowing users to first explore the simpler websites and then going through the more complex ones, or whatever their preference may be. And additionally, it future-proofs web searches as it sets a precedent for future AI-driven and user-centric search technology, which paves way for a smarter and more intuitive web interaction. Thank you very much.